lot of the data sources that power the site. And so if you think about the requests that come in from Hulu.com and various devices, a lot of them end up touching our services, and our services are the critical path for a lot of those requests. What is Hulu? So I don't know if we're pretty well known at this point, more so than a couple years ago. But we are an online streaming company, so we provide a lot of premium content, like television episodes and whatnot, and movies, available all online. And so we have a lot of licensing deals with our content partners, Fox, ABC, NBC, so that way you can see a lot of currently airing shows right on Hulu.com and various devices. And more eloquently, we help people find and enjoy the world's premium content when, where, and how they want it. And a little bit more about the tech team at Hulu. As I mentioned, we have a lot of services that we develop. We try and embrace the service-oriented architecture methodology. And we also follow the Unix philosophy. So if you're familiar with it, it's pretty much that we try and keep our services encapsulated in terms of functionality. Don't do too much at one time. Just kind of focus on a core problem and solve it well. And going along with that, we have a lot of small teams that are focusing on these different problems and making sure that we can actually get a really good solution that scales well, has good performance, and can handle the traffic. And going along with that also, we're really focused on using the right tool for the job. And as you'll see soon, we found that Cassandra fit our needs pretty well for some of these services. And there's no barrier in terms of business, bureaucracy, or red tape for us to use Cassandra. It's what worked well for us, and it carries through a lot of different services. We can use what actually solves our problems. And finally, we do a lot of cross-team development. We're all developing services, and there's a lot of common functionality. And there's also some DevOps-related devices. So if you go to Hulu.com and you're logged in, as you're browsing the pages, you can see progress indicators showing, oh, hey, you watched this episode, or you're only halfway through another. This is all provided via the HUGETOP service. And the other fun feature with HUGETOP is session carryover. So as you're watching a show on your laptop or something, maybe it's time to head out, time to head to work. So as you leave the house, you take your phone with you. As soon as you get on the bus, you take your phone out and you go to the Hulu app, you can pick up right where you left off. And that's all provided via the HUGETOP service API. Things that HUGETOP does not cover is a lot of the analytics work. Part of the process is HUGETOP is really related more to the real-time requests that come in, and we leave the analytics work to an entirely separate pipeline, which is built up around Hadoop. So ultimately what this means is we're not going to be running MapReduce jobs or using Spark on top of Cassandra. Cassandra is purely for low latency request serving and stuff that goes along with that. One of my favorite shows is Chicago PD. I'm from Chicago. So you can see one of the progress indicators down at the bottom. The little green bar just indicates that, hey, I've only watched maybe about 20 minutes of it, so I still have some entertainment left. I'm sure you're kind of anxious to see some of the specifics about Cassandra, but we'll get there eventually. The basic format of this is going to be, I'll go over the old architecture, then I'll touch on where Cassandra fits in the new architecture, and then we'll take a little bit of a look at the actual keyspace that we're using in production, and how we actually migrated all the existing data from the old service to the new service in Cassandra. And if we have time, I'll talk about some of the operational stuff that we've encountered with running Cassandra in production. Yeah, feel free to interrupt at any point. This is just a guideline in case you have some question. I may cover it in a slide. So it's just the idea of where we're headed. So the old architecture. The old architecture was based on MySQL. And so at the very top, you can see we have Hulu.com devices and then some other internal services that aren't exposed to the internet. They're just purely within our data center. So these are the three primary sources of web requests that come into HUGETOP. HUGETOP itself is really just a Python application. We use GEvent to make sure that it's async, and we can handle a lot of traffic. So as you imagine, this service is one of our busier ones at Hulu because there's a lot of people constantly watching videos. We're getting updates on where people are in videos, and we're also trying to service requests for like the various trades that you saw with the progress indicators. So there's a lot of concurrency in here, and we use GEvent with Python to ensure that we can handle extremely high load. Now, in terms of the actual data stores, the two data stores we use are Redis and originally it was MySQL. And the idea here is the Redis shards are there as pretty much caching. Now we did have persistence enabled, but we have a very large Redis cluster to handle a lot of that read load, and it handles quite a bit of traffic. And then on the other side, we have a Python application that is talking to the MySQL servers. And the actual MySQL cluster consisted of just 4 really beefy, big iron machines with 8 different shards on them. It's just very pure, simple sharding scheme. We take a user ID, mod by 4, and figure out what actual machine is going to handle that user's traffic, and then the application goes, connects, and gets all the data that it needs. Also, not pictured, this is multi-data center. So we have Redis masters in one data center, and they replicate to Redis slaves in another. And the same goes for the MySQL shards. We have MySQL masters in the same data center as the Redis masters, and they replicate to the other, just like Redis. So the new architecture, here's Cassandra. We got rid of the, there's not much different except for the bottom right corner. And we got rid of MySQL and the Python application that was directly talking to MySQL. And we replaced it with another API that we call Cassandra REST API. So if you abbreviate that, you get crappy. So we have the crappy API. And in terms of the actual storage, we went from 4 MySQL servers up to 8 Cassandra nodes. And there's actually 8 in our first data center and then 8 in another. So they're fully replicated. And the reason why we switched to crappy was because the Python drivers at the time were not very good for CQL. And at the point where we actually started working on this, it was a toss-up between Thrift and CQL, but going forward, we realized that CQL really had a better future than Thrift and wanted to embrace that. And so we went ahead and created a very thin API just with the DataStax Java driver, so we could use CQL.
Any reason why you need a bigger cluster for Cassandra than you used to use for MySQL?
Yeah, it's a very, very good question. One is we were running out of space with the MySQL servers, so we wanted to have a little bit of extra headroom at that point. And the other thing is replication. So with MySQL, we only had a master and then slaves. There wasn't 3 copies of the data, but with Cassandra, now we're going to hold actually 3 copies on disk, so we need more actual hardware for that.
Are you using a strong consistency using Quorum or
We use local Quorum. Yeah, the way that I'll discuss in a little bit the query patterns, but the idea is that we do local Quorum reads and writes. We want to make sure that when the data centers get cut off from each other, when they get isolated, that we can still service requests. So the switch. Yes, so this stream of data is ever growing. There is no stopping this. People are going to continue to watch videos, and we really can't purge any of this data. So we need a clear path of how we're actually going to scale this. Yeah, MySQL was working pretty well for us, but the servers were reaching 90% utilization, so we needed to get off of them as quickly as possible. And also, manually restarting is fun, said no one ever. And yeah, in terms of continuing to use MySQL, we would have had to provision more hardware and then redistribute all of that data. And so we would have had a lot of work ahead of us anyway. Instead of going through that entire process, we said, you know what, let's just switch to Cassandra and put forth that work to something we can actually scale continuously. So the choice on Cassandra, as you can probably imagine, and I'll show you shortly, our data model is actually pretty simple. There's not much complexity to managing where people are in videos. It's very straightforward data. And it fit very well to Cassandra. We looked at HBase and RIAC and a couple others, and there were drawbacks to all of them. When we initially did this, HBase wasn't highly available, or HBase relied on HDFS, which was not highly available due to the single name node issue. That's since fixed, but yeah, too late. So yeah, RIAC just didn't have the performance we were looking for. One of the big things that we really liked about Cassandra was that it was highly available. And it's not just for the cases where servers fail. It's really, really nice to have a database where we can take a server offline, upgrade it, tweak some GC settings, or make changes without having to totally take a master or a slave offline. And going along with the entire idea of Cassandra, no node is special. They're all pretty much the same. So it's not like we have some sacred master like we have with MySQL where we can't touch it at all. It's got to stay up, because if it goes down, we have a lot of work to recover. The complexity here is with how Redis and Cassandra talk to each other. And the basic idea is we have 2 high-level queries that come in. We have the actual video position updates. So the players on, like the video players on Hulu.com and the devices send beacons to HUGETOP every 90 seconds or so. And then also whenever the player closes. So we have this massive stream of position updates that come in. And what happens there is, first we write it directly into Cassandra. After that, then we update Redis. And that's the entire write path. For the read path, what ends up happening is, first we check Redis. Super fast. If Redis doesn't have the data, what ends up happening is that we have to go get Cassandra, then queue a job and say, okay, offline, not offline, but asynchronously, we have to go and update our Redis cache. And then we return the Why it happens asynchronously is because the work that we end up having to do to update an entire user's history in Redis is way too long to do in our critical path. So the user doesn't want to have to wait 100 milliseconds for us to update Redis when we have the data available immediately. So we take that data, say, okay, we'll do this later, but we return as soon as possible, as soon as Cassandra has it.
I have a question.
Yep.
So in the old slide, where you were using MySQL, you were using Redis as a persistent enable. Now in the new one, you are using as cache, right?
Right.
What was the reason actually?
Yes. So we realized that we really didn't want to rely on Redis as a pure data store. Sure, it has persistence and can handle quite a bit of load. But we weren't really happy with the persistence models there. There's RDB and append only files or whatever. But it didn't have the same actual durability that Cassandra could offer. So we figured, let's not even use Redis for that persistence. Instead, we'll use Cassandra purely for persistence and let the Redis cluster act simply as a cache.
Is it LRV mode? So do you talk these? Is it on LRV mode?
Yeah, that's one approach. Yeah, we strive to maintain as close to the entire data set as possible in Redis, which is a lot of memory. Yeah, just summing it up, we have Redis is actually acting as a cache. The main feature there is we're using its data structures to have better indices. Some of the indices are like, show me the last 5 videos viewed by somebody, some extra information about show, metadata, that sort of thing. And we can use Hulu with Redis to solve the join issue that Cassandra doesn't have available. And when the Redis cluster, if we do a rolling restart and cluster nodes go offline, then we just rely on Cassandra to rebuild the Redis.
So how do you deal with that cold start problem? If something,
I'm sorry.
so when Redis node goes down, is it like a spike in dependencies when you read from the
Yes, there would be a spike because now instead of having cache there, now everything starts falling through to Cassandra.
Do you have replicas in Redis?
Yes, yeah. The setup is that we have 64 Redis masters and 128 slaves, I believe. So I think we put a slave in both data centers.
So the data model between Redis and Cassandra is the same?
Yeah, the way to think about it is that Cassandra stores the raw data. There's no metadata, there's no extra indices. All of that extra data is also added within Redis. So we're not actually storing the raw data within Redis.
This one is column oriented, the other one is key value.
Yep.
And different map.
Yeah, the model fits Redis pretty well, actually. So, we can have various data structures that represent a single user's videos. There's maps and sets and all sorts of things within Redis to make it work. So the data model within Redis is actually much more rich than Cassandra.
So do you have a data access layer on top of the two databases?
HUGETOP negotiates that directly. So yeah, when requests come in, HUGETOP actually makes the connections to Redis or makes the connections to Cracky and figures it all out. Okay, so hardware. We initially started with some Hadoop machines. We had some spares available, and we got them provisioned. And just a pretty standard box. They were physical, no VMs. Didn't want the overhead of having a Zen hypervisor or something sitting in the middle. We wanted to actually have the JVM run directly on the hardware. And just 6 hard drives, nothing special there, 32 gigs of RAM. we were using leveled compaction and just treating those 6 drives as a JBOD. There was no RAID, no software RAID, no hardware RAID. It's very simple. And we ended up using leveled compaction there because we could get very good distribution of data across all 6 drives. We didn't have to worry about really large SS tables building up from size tier compaction or something. We had very little ones managed almost, very evenly across all 6. And this worked pretty well for the writes. We had done a couple imports to test performance, and we were very happy with how the writes were looking. But then we actually went to query the data, and not so happy. What ended up happening there is there was a lot of disk I/O that ended up going on, and the disks simply couldn't keep up because you're limited to only 100 IOPS or so with a standard drive, so there just wasn't enough horsepower available in the cluster to deal with it. So take 2 was to switch to SSDs. And the approach here is that also went with physical boxes, but the catch is we also realized that we had to disable C-states. So if you're familiar with C-states, it's pretty much what your laptop does, but for servers. What your laptop does is when it's sitting here, it downclocks the CPU. So really, we were only running at about 60% of the power available, and we want it to be at 100%. If there's any spare time available, we want it to be at full power. And kind of an interesting story there is being on the core team, we're super interested in minimizing the latency because all of our services are in the critical path. And with that, we kind of had a little competition going within our team of who could make their service the fastest. So, we improved things a lot, and we started to look at our graphs. And as we started to reach peak hours, the RPS, the request per second, would start to go up. But then latency would actually decrease during peak hours. We're like, let's add more traffic. I mean, if we can get lower latency just by throwing more RPS at it, it's a big win. What was actually going on there was during peak hours, the CPUs started to bump up their frequencies, and as soon as they did that, latency started to go down. So instead of waiting till peak hours to get low latency, we just automatically scale them to 100% out of the box. RAID 5 consideration there is that we want to tolerate failure pretty well. It's way easier to rebuild the RAID array with a single failed drive than it is to let Cassandra have to shuffle data around and run a repair. It's just way faster if the RAID controller can just copy the data from other local drives and be done with it.
So does the RAID can help?
Yeah, RAID can helps for sure. We didn't end up going with that because as you start to calculate the replication, we have 3 replicas already times another data set. So we have 6 replicas. If we went with RAID 10 and all the drives, then we'd end up with 12 copies of data on disk, which is pretty excessive.
Why do you have more RAM here? 48
Yep. Redis, or sorry, not Redis, Cassandra, Redis likes RAM too. Cassandra likes a lot of RAM for the OS. The OS will eat all of it up for the page cache and make things faster just because the OS will then hold data in RAM and not have to go to the SSDs to fetch it.
So you already use pretty much all the RAM?
Yes, if you, I don't have the graph here, but we can watch the file system buffer usage over time, and you can see it increase very sharply as, right after a restart, as the SSDs start pulling in more data, it gets held in RAM, so that way any subsequent requests for that data can just be serviced out of RAM rather than hitting disk again.
I had a question about rebuilding a RAID 5. What kind of terabyte size was that time? Since you said it was easier to rebuild it.
Yes, we haven't had to try it with those particular ones.
Right?
We've initialized them, and we can pretty much write to all the hard drives you know, you can zero out the entire array in 15 minutes or so, which is pretty good. So we figured under load, maybe an hour, maybe more. But in terms of rebuilding with Cassandra, having to stream it over the network from other nodes, that would take significantly longer. Yes, the keyspace design. There's two different sets of queries that we want to handle. One is those queries that I was talking about before. Hey, tell me the last position for user X, video Y. Very, very straightforward. Just have a simple views table where the user ID is the partition and the video ID is the clustering key. A couple attributes extra to store along. We thought about trying to use a blob to hold all that data, but the issue with trying to hold it all as a blob is the read, modify, write cycle, like you may have just heard from the previous presentation. And so with this, if you actually split up the individual attributes, then you can update them individually, not have to worry about any read, modify, writes. And the other case is for a daily log that we had to provide to another service. So part of our recommendation team gets of all the views, so that way they can use this to train their models and figure out the recommendations to use for the next day and to incorporate it into any other of their real-time services as well. And with MySQL, what we would do is every single day we would run a select star from viewed videos. And they would have to scan through the entire data set on all of the MySQL servers. And we had to do this every single day, but MySQL actually ended up taking 30 hours to execute that query. So that's a real uphill battle if you can't even complete the job on time. So the way that we approached it this time was that every single day we say, okay, there's going to be 128 rows designated for holding the views that come in. And so with these views, or with all those rows, what we do is we just have some very simple sharding scheme where we write pretty evenly to all three of them, or all 128, just as we would shard to the MySQL servers. And this way, rather than saying, okay, we'll just have one row that holds the entire day's worth of views, you know, we split it up to 128, and we get really even distribution. Now, in terms of actually querying it, we actually just do 128 little range scans. And because the rows are spread across nodes, we can actually distribute the load very evenly.
So how many nodes do you have in Cassandra? 8, right?
Yes, 8.
Then why it's like so big to 128? You may have maybe 16.
Right. The main motivation for 128 is the rows get very large, and we wanted to try and keep them as small as possible, because when we do these select stars, they still end up returning a lot of data, and if we can split it up into smaller ones, we can kind of prevent Cassandra from having to move a lot of data around.
This data, these views are per user, right?
Yes.
And you can also have, instead of this random keys, maybe the user ID, like user ID along with the data, right? Instead of this random partition.
Right. So we do the partitioning based on user ID. So we just modify 128, and that determines which of the 128 rows is going to hold that particular user's data for that day. And so the next day we start a whole other new 128 and keep on going every single day. And the way it ends up working is that we have a TTL on it as well, so I don't know the exact number offhand, but eventually the old rows just start dropping off the TTL clip, and we recover all that space.
That answers the question.
Gotcha.
You can use the number from 2 bit.
Too big? I don't know what the mean size is on it these days. I'm sorry. I figure.
1,000 or 100?
Yeah, we want to keep it to like under 100 megabytes for sure, like per room. So with 128, we get a lot of room to play, and we can change it every single day. It's not like we're locked into 128. If we realize that these rows are too big, we can just say, all right, tomorrow we're going to try 256 and see if that helps. And it actually only takes about 5 minutes then to query a day's worth of data. So, big win. We're running out of time, so I'll skip over the migration. The migration was really simple. The big factor there is that we can exploit timestamps, the column timestamps, to help with consistency. So when we we replicate data to the Cassandra cluster, and then we have to backfill the data from MySQL into Cassandra. And if we are very careful with the way we specify the column timestamps, we ensure that all the new data that we started writing to Cassandra doesn't get overwritten by the old data that comes into Cassandra from MySQL. Big thing there is time. Very helpful.
Yes.
Operationally, Cassandra is very smooth. We haven't had too much issues. Use a internal tool for automating the repairs. Every 7 days we try and run a full repair around the ring. And standard GC time, GC pretty second, 10 days I think. Metrics. One of the cool things is with the metrics library that Cassandra uses is that you can hook into it directly and get access to all of the internal metrics. I think there's a blog post on the DataStax blog about it. But this way we have access to all the histograms for the latencies of every single column family on every single node, as well as data sizes of the column families, number of connected users, so forth. It's extremely helpful to have this data when you try and troubleshoot issues, because you can pinpoint the exact cause and dig into it very, very deeply because of the sheer number of metrics that it exposes. But the big problem there is it exposes so many that it actually overwhelms Graphite. And to give you an idea of how much data there is, originally we were sending metrics from Cassandra to internal metrics from Cassandra into Graphite once every 10 seconds. And we were sending roughly 10 megabytes per second of metrics just into Graphite. So the volume of data from the metrics alone was a sizable fraction of what some of the nodes are actually dealing with for the queries. And, not very interesting, I guess, for the monitoring that we do. You can pretty easily tell if something's going wrong if you look at some of these Graphite graphs and see, there's an increase in the number of hints that some machine sees or is holding on to, that sort of thing.
Do you do any alerting also?
Yeah, we have an internal tool as well at Hulu for e-alerting, and so it's super easy to set alerts based on Graphite graphs. These exceed some threshold that we set, and so having all the data available within Graphite makes it really easy for us to use existing tools at Hulu. Yeah, so the parts that haven't been smooth for us with Cassandra is we run into SS table corruption a couple times, and it hasn't been hardware related. So there's been a few bugs within Cassandra, which you have to be very, very careful of. There's some race conditions, and also I know there's some instances within early versions of 2.0 that have seen some corruption as well. So it's not 100% bulletproof. And when we do see a bug, there's two tools that we go to. One is no-tool scrub, and the other is SS table scrub. The first one, no-tool scrub, pretty much what happens is you can connect to a live node and that live node then itself executes a snapshot and then starts cleaning up the SS tables. And with SS table scrub, you do it offline. So the node is actually going to move down when you do that. The reason why I say if things are really, really bad, you use SS table scrub is a couple of weeks ago, we ran into an issue where Cassandra wrote out a bad SS table, and as soon as it tried to read it, it was trying to allocate some very large byte buffers, and in doing so, it was causing Java keyspace out-of-memory errors. And as soon as that happened, Cassandra would crash. So every time we tried to restart, Cassandra would crash again. We had to run a SS table scrub on that. Cleaned it up, started up fine, back in business. Yep.
So because of this SSO corruption, they lose data. Data is lost.
It's not lost. So
All because of Java?
so as soon as we run a scrub, it's also good to run a repair. So that way, we have 5 other copies of the data available, and then you can pull in.
Also, I thought maybe this data is replicated immediately, right? That means whatever corruption happened on one node might replicate to.
Yeah, the issue that we were seeing was that Cassandra simply couldn't read it. And so with that data, it's as good as being not there. And that's actually what the scrub tools do, is it simply just gets rid of that data. So Cassandra, via the anti-entropy session, realizes, hey, that data is not there, and then just pulls it in from some other replica. And finally, there are things to watch for. Snapshots are awesome, but they burn disk space really, really fast. So with the no-tool scrub, it does a snapshot, and then it rewrites all the tables. And if you know what a snapshot does, it hard links all of the existing files. And so initially you have no extra space, because really the snapshot is a directory of hard links. But when no-tool scrub starts copying the new files, then suddenly you have 2 copies of the data. And because of this, you want to make sure that you're always under 50% disk utilization. In case you ever have to do one of those, you want to make sure that you can have an entire other copy of your data sitting around. Because if not, then you have to be very careful with probably cleaning up the snapshots as the scrub is running, or do it column family by column family. And last slide. The performance of Cassandra is really, really good. But during our import, the initial import of the MySQL data into Cassandra, we were running into some issues with GC. And we ended up figuring out some settings that allowed us to get G1 GC to outperform concurrent market sweep. And from the graph, you can see that the green line up top is G1 GC, and the bottom one is CMS. And the graph, sorry, it's small to read. The graph is us doing a small import of the entire data. We said, okay, let's see how it performs. Let's try and improve it. And we ended up running it for about 8 hours. And with this, we can see that G1 GC is consistently higher than CMS. And we were surprised with how well it performed, actually, because CMS is pretty much the go-to garbage collector within Java. So it was a good win for us. So thank you for attending my talk.